So this problem has us trying to first determine the resultant force vector from three forces applied at a single point. So this is an equilibrium, a particle equilibrium problem in the end. But first of all, we'll find the resultant force vector. And recall that a resultant vector is simply the vector sum of all of the forces. In other words, it's one single force that equals all three of those force contributions. To do this, we'll first do this with vector addition. The second way we'll do this is with Cartesian force coordinates. In other words, we'll break this down into x, y components for each force. And then in the end, we'll find our reaction force using our resultant force vector. So for part A, vector addition. Now this is arguably the more time-consuming and possibly the more difficult of the two approaches between this and breaking it down into force components. However, it's useful to know, and in some cases it's quicker and easier than the force components, and it's really a user's choice which one they prefer to use. So first step, we need to understand that if we're adding three vectors together, we need to do this by first adding two of the vectors and getting an intermediate resultant vector, and then to that intermediate vector we'll add the third vector and find our final value. So first, let's add vector 1 plus vector 2 to get a new vector that we'll call fr prime. And the little arrow on top denotes it's a vector rather than a scalar. So recall that a vector has both magnitude and direction, and the scalar only has magnitude. In order to add these vectors, we'll employ the parallelogram rule and the vector triangles to determine both magnitude and direction. So first, if we want to draw our parallelogram, let's sketch our axes here. And we know that if we're adding force 1 and force 2 together, we can draw force 1 coming off of that axis. It comes out 8 newtons at a 45-degree angle. Now this angle here will be 90 minus 45, which is 45 degrees as well. To that we can draw in force 2. And this one is 5 newtons. And the angle between the horizontal and the vector is 30 degrees. So we already said that this is 45 degrees. Now with the parallelogram rule or law, whatever we call it, we basically are going to draw this vector at the tip of the other vector. So we draw a parallel line to that vector there, and we draw a parallel line to this first vector at the tip of the second vector. And they intersect at a key point here. Where they intersect is going to be the end point of our sum vector, of our vector sum fr prime. So if we connected a line all the way up to this point here and drew an arrow there, the magnitude and direction of this is fr prime. And that's what we want to determine, fr prime. So this is our parallelogram. And to it we can add all the possible information that we know. So let's do that before we move on. We can say that F2 is here, and this is equal to 5 newtons. And these drawings can get a little bit busy, but we'll try and keep it as clean as possible. We know that we have this line is parallel to this line, and this is 8 newtons in magnitude. And this line here is parallel to this line, and this is 5 newtons in magnitude. And we can get some angles out of this as well. So let's try and pick a color we haven't used. quick black. And let's call an angle here. Let's see what we call this angle. Well, let's just calculate this directly. This angle is 30 degrees plus 45 degrees is equal to 75 degrees. It's the angle between force 2 and the horizontal and force 1 and the horizontal. And since we have a parallelogram, this angle here is also 75 degrees. Now there's two other angles here. Let's call this one alpha r prime, and we'll see why in a minute. And this one here is also alpha r prime. So alpha r prime, what is that value? Well, we can get that quite simply. We know that there are 360 degrees in a four-sided shape in a parallelogram. So that's equal to 2 times 75 degrees, this angle plus this angle, plus 2 times alpha r prime. And if we solve for alpha r prime, we can get 105 degrees. And right now that's about all we can get out of that shape, which is quite a bit. The only thing that we're really missing is the magnitude of f r prime and the angle at which it acts. So to get that, we're going to draw a vector triangle. Now we have two vector triangles in the shape, and both of them are essentially identical, but they're sort of flipped. We have this f2, f1, fr prime vector triangle, and we have this other one which is f1, f2, fr prime. And it doesn't really matter which one we choose, but we'll draw one of them out. I chose the top one for this example. And when we draw it, we try and keep somewhat consistent orientation and magnitudes in order to more easily visually check our answers and to appropriately solve this. So that wasn't very well done, but it's not bad. We can say that this angle we've already solved for is 105 degrees. So this angle here is alpha r prime. And we named it that because we have a vector here, fr prime, and the angle opposite to that line is named after the line. So we name this angle r prime. And we have two other vectors here. We have force 1 is equal to 8 newtons, and force 2 is equal to 5 newtons. Opposite of force 2 we have, let's call this alpha 2, and opposite of force 1 we have an angle, let's call it alpha 1. So in order to solve for the unknown quantity here, which for us right now is fr prime, and later we're going to get alpha 2 as well, we need to employ some of our trigonometry. And we know that we have a cosine law. So cosine law states that the length of the third side of a triangle is equal to the root of the other two sides squared, the sum of the other two sides squared, minus 2ab cosine of that side's angle. Now, we can write this out in terms of fr prime is the unknown quantity and see where we get with that. Fr prime is equal to the root of the sum of the square of the other two sides, f1 squared, plus f2 squared, minus 2 f1 f2 cosine alpha r prime. Cosine of that side's angle. This side's angle is alpha r prime. Now we simply need to expand this and plug in our values. So we can write fr prime is equal to the root of 8 squared plus 5 squared minus 2 onto 8 onto 5 cosine of alpha r prime, which we've calculated to be 105 degrees. And we can say that fr prime is equal to 10.474 newtons. So that only solves part of our problem. Let's have another look at that vector triangle. If we want to determine the vector properties of fr prime, we not only need its magnitude, but we need an angle at which it acts. We've already been given the angle at which f1 acts. We can recall that we have an angle here of 45 degrees off of the vertical. So if we found the magnitude of alpha 2, we could calculate the angle fr prime acts off of the vertical, or off of the horizontal, or off of any other angle if we wish, quite simply. So let's find alpha 2, and to do that we'll employ the sine law. So both the cosine law and the sine law work by understanding that if we know any 3 properties of a triangle, we can solve for the other 3 using trigonometry. So the sine law says that the magnitude of a side, fr prime, over its angle, the sine of its angle, sine alpha r prime, is proportional to the magnitude of another side over the sine of its angle. If we're trying to solve alpha 2 in this case, we're going to use the magnitude of f2 over sine alpha 2. Now we can rearrange to solve for alpha 2 quite simply. If we bring it to the other side and take the arc sine of both sides, we can say that alpha 2 is equal to the arc sine of f2 over fr prime times sine alpha r prime. And if we plug in our values, we can say that alpha 2 is equal to the arc sine of 5 over 10.474 sine 105 degrees. And this gives us alpha 2 is equal to 27.46 degrees. So at this point we're going to want to draw in our intermediate step resultant vector fr prime and its angle, along with the third vector f3, and look at what we need to add together, and then follow very similar steps to get our final value. So let's draw what we have right now. We'll draw our system with our intermediate step vector replacing f1 vector and f2 vector. So we can draw our axes roughly in here. And we know that we've just calculated this vector here. Let's draw it in green, coming off at an angle fr prime is equal to 10.474. So this is what we've just determined. It replaces f1 and f2. It's the vector sum of those two. And we know a couple things. Well, we can find some angles in here. We can find an angle, let's call this one theta r prime is equal to 45 degrees plus alpha r prime. Now that 45 degrees, let's put on our original drawing right below this. So we're taking this 45 degree angle and adding to it the angle between F1 and FR prime that we found below that to determine the new angle at which FR prime acts. And this is equal to 45 degrees plus 27.46 degrees. Theta r prime is equal to 72.46 degrees. Now, when we name our angles, thetas and alphas and betas, we're inventing those names ourselves. So there isn't really a system as to which one to choose. I chose theta in this case. The subscript sort of denotes what we're measuring, and thetas, alphas, betas are usually reserved for angle quantities. But this is up to you. You could name it anything you want as long as it's clear what you're indicating here. Let's determine this angle too. This angle here is simply 90 minus theta r prime, and this happens to equal to 17.54 degrees. So FR prime is 17.54 degrees off of the horizontal, or 72.46 off of the vertical. Now we have another quantity here. We have F3. And we know that F3 is equal to 11 newtons. This was specified in the problem. And we have an angle at which it acts. This angle is 20 degrees off of the vertical. So now our task is to add FR prime plus F3 to get the resultant vector. To do this, we will so now we find FR is equal to FR prime plus F3. And to do this, we'll employ our parallelogram law as well, and we'll draw in our vectors. So let's start with drawing in F3 here, and to that we'll also draw in FR prime, FR prime is equal to 10.474, and F3 is equal to 11. Now, with our parallelogram law, we simply need to draw the line parallel to this vector at the tip of the other vector. And the same thing on the other side. We can say that this line is parallel to this line, and this line is parallel to this line, and this gives us some information. Well, first off, we know that the vector sum of a vector going this way and a vector going this way will be something in the middle, and it is essentially joining where those two begin, intersecting by where their parallel lines intersect. Parallel lines. And we can say that this vector has a magnitude of FR. Now, similarly to what we did before, we should take the opportunity to solve for some unknown angles that we'll use in a little bit. If you don't do this step right now, it's easy to come back to it when we know which angles we'll want to use. So first off, let's draw in our axes here, and let's label a couple things here. I'm going to give an angle here, give this one the name phi. And if we look at what will become our vector triangle, what's shown here, you have FR, you have a triangle form FR, FR prime, and F3. If we look at that, we can say that this angle here is named after the side FR. So let's call that angle alpha R. And then we know that this angle here is also alpha R, and this angle here is also phi. Now we have enough information to calculate phi, and using phi we can then calculate alpha R. So we know that phi is simply equal to 90 degrees from here to here, plus 20 degrees from here to here, plus 17.54 degrees from there to there. 90 plus 20 plus 17.54 degrees. Phi, in this case, is equal to 127.54 degrees. Now, what we're most interested in is alpha R. So let's calculate that. And we know that there is 360 degrees in that shape, and that's equal to 2 alpha R plus 2 phi. So alpha R is equal to 360 minus 2 times 127.54 over 2. Alpha R is equal to 52.46 degrees. Alright, so at this point we're now ready to draw our vector triangle and try to determine the magnitude of FR and the direction of FR. So now, draw our vector triangle. And this vector triangle will consist of sides FR, F3, and FR prime. So to do this, let's sketch it in. And we know that we're going to take the top, I'll put this up here, the vector triangle. For this drawing, I'll just use this top triangle here. Let's draw that in. We'll start with our force vector here, our resultant vector, FR, and then we have a FR prime vector, and we have an F3 vector. And F3 is 11. FR prime is equal to 10.474. And we don't know the magnitude yet. This is 11 newtons, and that's 10.474 newtons. We don't know the magnitude of FR yet, but we do know one thing. We know the angle here, alpha R, is equal to 52.46 degrees. And then we can draw in some other stuff that we don't know. A little bit later we're going to need this angle here, alpha 3. Turns out we don't need this angle here, so we'll leave it out for now. So to get FR prime, or FR, we can employ the cosine law. Now remember, if we have 3 known quantities in a triangle, we can solve for the other 3 using the sine and cosine law. We have an angle and 2 sides, so we can solve for the opposite side to that angle. So we can say that FR is equal to the root of f3 squared plus fr prime squared minus 2f3 fr prime cosine alpha 3, or sorry, not alpha 3, cosine alpha r. And we know every term under the root, so we can solve for this. I'll do it down here. So we have space fr is equal to the root of f3 is 11 squared plus fr prime squared, 10.474 squared, minus 2 times f3 times fr prime cosine alpha r, which is 52.46 degrees. If we solve for this, we can say that fr is equal to 9.503 newtons. So now all we're left to do is determine the angle of that force vector. We have the magnitude, and we need the angle at which it acts. We happen to know the angle that fr prime acts off of the vertical. We know this angle here is equal to 72.46 degrees. This was calculated previously. If we can find alpha 3, then we can easily define fr in terms of any known angle. So let's do that. And to do that, we'll employ our sine law. So we can say that, once again, the ratios of sides, so fr over the sine of its angle is proportional or equal to f3 over the sine of its angle. So we have this f3. We need to calculate alpha 3. We have fr and we have f2 or alpha r. So we have all the information we need to solve for alpha 3. If we rearrange this for alpha 3, we can say it's equal to the arc sine of f3 over fr sine alpha r. Alpha 3 is equal to the arc sine of 11 over 9.503 sine 52.46 degrees. And alpha 3 is equal to 66.61 degrees. So now we've essentially finished the problem. The only thing that's left for us is to draw the resultant vector and the angle at which it acts. So let's begin. We'll sketch in our coordinate system here. And then we'll draw in our vector, and this vector here is coming down and to the left. It's coming down and to the left like FR. FR is equal to 9.503 newtons. And then we have a couple angles. We can define an angle beta here. And if we recall, there is a standard sort of XY coordinate system that we use. Let's draw that over here. X, Y, And starting at the x-axis and rotating counterclockwise, we have theta. And this is positive. Theta moving off of the x-axis, rotating counterclockwise, is a positive value. So if we want to get our standard angle here, we can calculate theta as well. So beta is simply calculated as alpha 3, 66.61, minus the angle between FR prime and horizontal, and that angle is 17.54 degrees. So beta is equal to 49.07 degrees. And if we know beta, we can get theta is equal to 180 degrees plus beta. Theta is equal to 229.07 degrees. And we are done the problem. So in the next video we'll look at how to solve this using Cartesian force coordinate systems. In other words, we'll find it with fx components and fy components, and then convert that back into a vector system at the final answer.